is 0. It's non-existent. There is no molecular polarity, which is why it's non-polar. So we just say its net dipole is 0. So now let's look at the valence bond diagram. So nitrogen is a 2s with 2 and a 2p with 3. So what we have are the 3 singles up here are these 3 singles, and they participate. But we've also are including the 2 in the s. This s orbital with 2 electrons is now being forced to bond. So you have to include it in your diagram. So let's start with nitrogen and the 3 p orbitals. So I'm going to draw one here with an electron, one here with an electron. So this is the one to the right, this is the one to the bottom, and then this is the one to the left. So these 3 singles are these 3 singles, and you don't have to worry about this stuff up here. It's just the other part of the p orbital. But the s orbital is also participating. So I'm going to draw that in a different color. The s orbital is somewhere up here in this 3-dimensional mess, and it has 2 electrons in it. So this is the s orbital of nitrogen. Okay, and we have to draw it in because we're actually using it to bond with the oxygen. So now all we do is bring in our oxygens. So switching colors here. So on this single electron, we're going to draw 1 p orbital because we filled the other one by adding an electron. So we're just going to draw 1 in here with its dot that it brings in, and then we'll put the 3 pairs around it. So if you look at an oxygen is a 2s with 2 and a 2p with 4. So it normally has 2 half-empty p's, but what we did is we added 1 here. We filled this one. So now we only have 1 participating here, and that's the one that we're drawing. The other 2 p orbitals are represented by just the pairs, and then there's its s orbital that's there. This oxygen has both its p orbitals. 1 will go to this electron on the end, 1 to that electron. So we're going to draw 1 here, and we're going to draw 1 here. So as long as your dot is somewhere in your Venn diagram here, so to speak, I don't really care. I just want you to know that this 1 electron comes from the N, 1 from the O, 1 from the N, 1 from the O. They're both p orbitals, both half-full p orbitals of the O's participating, and then the 2 lone pairs, 1 from the 3rd p orbital, 1 from the s, don't participate, so we just draw them in like that. And then the last thing you're going to do is put your square bracket and a negative around it. So that's what NO3 looks like. So that one's a little bit more complicated, but again, this just follows this: 3 singles, 3 p orbital singles, 1 pair from the s, 1 pair in the s orbital, and then this oxygen has its 2 half-full p's bonding to the N. This oxygen has its 1 half full p bonding, and then this oxygen we still have to add yet. This oxygen here, we emptied that p orbital. Remember, we shifted it over, so that p orbital is going to come in empty, and now your valence bond diagram is complete. Okay, I didn't put a pink dot in there because we took the electron from the p and shifted it over. Okay. All right, number 7. Okay, number 7, we're going to do HSO3 minus. Okay, so one of the rules to follow, this is another rule from grade 11, okay, is that oxy polyatomic ions and oxy acids with an H, okay, have the H bonded to the oxygen. Okay, so that's the rule to follow. So if you have an oxy polyatomic ion, which is what this is, or an oxy acid, and we'll do one of those as well. And if they have an H, all acids will have an H, but if your oxypolyatomic ion has a H, that H has to be bonded to the oxygen. Again, this is a rule from grade 11, but just to refresh your memory on that. So your central atom here is going to be S, because there's only one of them. You have 3 O's, so the 3 O's have to be bonded to the S, and then the H is going to be bonded to one of those O's. So our S has 6 electrons, and we have to put 3 O's around it. So let's put one here. We'll put one over here, and then we'll put one over here. Okay, so looking at this, let's start with a negative, means we have to add an electron. So we can kind of see that this oxygen here can bond to this sulfur here. This oxygen can bond to this single electron on sulfur here. The problem over here is this one. This has 2 singles up against a pair. So one of the things we're going to do is we're going to leave this one for right now, and let's add the electron here. So now what we're going to have is this oxygen can bond to this single electron on the S. Then if we put the H here and bond the H to this O, we have a problem where we have a single electron up against a pair. So let's put the H over here. And now what we're going to get is this will bond like that, and this O to S there. And now you should know that this will shift. And when we shift that over, so this is a shift, we're now going to get this pair bonding with the empty p orbital of an O. So now we have to go to Vesper. So we have 2 central atoms. We have the S and the O. So let's start with the S. So let's cover up the O and what's bonded off of it. So this S has 1, 2, 3 bonded pairs and 1 lone pair. So let's go over here. 3 bonded pairs and 1 lone pair, trigonal pyramidal at 107.5 degrees. So trigonal pyramidal at 107.5 degrees. Let's cover up the S and what comes off of it. Look at the O. The O has 2 bonded pairs and 2 lone pairs. So we've seen this one before, 2 and 2. It's bent or V-shaped at 104.5 degrees. So bent V-shaped at 104.5 degrees. So now when we go to draw this to Vesper shape, let's cover this up. Let's start with the S. So the S, we're going to have a lone pair. It needs to be trigonal pyramidal. So we're going to put an O down here with 3 lone pairs on it. We're going to put an O down here with 3 lone pairs on it. And we're going to put an O over here. Now before you put on the lone pairs, let's go to the O. This O has to be bent or V-shaped. So are you going to draw the H down here? If you do, it's going to interfere with this oxygen. So what you're going to do is draw the H up here, like that. That is still covering this up. That is still bent or V-shaped. So we're going to put the lone pairs to the outside here. And so that is your Lewis diagram to proper shape for the bisulfite ion. Okay, so now let's determine molecular polarity. This will be a little bit more complex. So you have a positive here, a negative, a negative. So all your O's will have negative charges around their electron pairs, and then this is going to be a positive because sulfur is less electronegative than oxygen. So let's put in our little dipoles. So this one will head towards the O, this one will head towards the O. So just based on those two, they're going to kind of go straight down. This one goes straight down, and this one goes this way. So if you look at this central atom, this dipole is going to go straight down, and on this central atom, this dipole is also going to go straight down. So the two of them both going straight down means that your molecular polarity is going to be straight down, or very close to straight down, close enough. So dipole is greater than 0. This is polar. Okay. So I mean, if you wanted to draw all of these out, you could. You'd have one going this way, then this one adds on that way, and then this one adds on this way, and then this one adds on this way, and so you're getting something close, very close to being straight down. Okay, so straight down, maybe slightly to the right, but close enough after you get those drawn in. Okay, so now what we're going to do is the valence bond diagram. So with the valence bond diagram, let's start with S. So S is a 3S with 2 and a 3P that looks like that. Okay, actually one more. Okay, so your sulfur has 2 singles, so there's our 2 singles and our pair in the P, and then the pair in the S, and then our oxygens each have 2 singles, and one of them got filled here, and this one we shifted 1 electron out of one P and put it in the other, so this P orbital is sitting empty. So let's start with the sulfur. So the sulfur, we're going to have a P orbital here with 2 electrons in it. That's this one. We're going to have a P orbital here with 1 electron in it, and we're going to have a P orbital here with 1 electron in it, like that. And so what you end up with now, and you put the pair up there, is you can bring in this P orbital of the oxygen, and you're going to bring that one in empty, because we emptied it out. So this S orbital is full, the P orbital is full, because remember, for an oxygen, it's a 2S with 2 and a 2P with 1, 2, 3, 4. It looks the same as sulfur, except it's one period up. So what's happening with this one is we took this electron and shifted it into this P, so that filled that one and kept this one completely empty. That's what this one is. This electron here, what we did is we added an electron to one of its P orbitals. So this one sits half full, and that's the one that's going to bond with the sulfur. 1, 2, 3, 4, 5, 6. And then this oxygen here, one of the P orbitals goes to the S, but the other P orbital goes to the H, which on our Lewis diagram needs to be up here. So 1 goes to the S, 1 goes to the H, and then the H we're going to draw in. H is always an S with 1 electron. Throw it in brackets with a negative, and that's your valence bond diagram. So this is identical to this, but instead of sticks, we're just using the shapes. And if you just get rid of the second half of these P orbitals, if you could hide them, then you can see this a little bit better. There's your 1, 2, 3 bonds, 1, 2, 3 bonds, where oxygen bonds, and then oxygen bonding to the S, oxygen bonding to the S, to the sulfur, and then to the hydrogen. So that's what that one looks like. Okay, let's go to, we have 2 left here. Number 8, so PO4, 3 minus. So your central atom is a P with 5. You're going to put 4 oxygens around it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Remember, you fill up with 4 singles and then you pair up, so your pairs will always be side by side. So that's what that looks like. So now you got to add 3 electrons. Well, we already know that this is up against a single, this is up against a single, this is up against a single, this is up against a pair. So we're not going to touch this one. So we're going to add 1 electron here, 1 electron here, 1 electron here. And remember, oxygen is a 2s with 2 and a 2p with 4. So what we're doing is for all 3 of these, we're adding an electron to one of its p orbitals, which means only one is now going to participate in bonding. This p orbital will no longer participate because we've just filled it. So what we're going to do now is form bond, bond, bond. Now we have to force the s orbital. So remember on phosphorus, we have a 3s with 2 and a 3p, each with 1. So 1, 2, 3 singles, 1, 2, 3 singles, but now we're going to force the 2 electrons in the s orbital to participate. So to do that, what we're going to do is we're going to shift, and then we're going to form a square bond, a coordinate covalent bond, which is just another single bond. So that's what that will look like. So going to VSEPR, we have 4 bonded pairs and 0 lone pairs because we're sharing that lone pair in a bond. So 4 and 0 is right here. 4 bonded, 0. It's tetrahedral. So again, 1 up, 1 to the right, 1 to the left, and this one is coming straight out at you. So we're going to have a P with 1 up here, 1 out here, 1 down here, and 1 over here. So square brackets, 3 minus. This is tetrahedral, and the shape is 109.5 degrees. Now let's look at our molecular polarity. Oxygen has a higher En than phosphorus, so we're going to put negatives all around here. And we have no positives, so we have no dipole. We can't go from a positive to a negative when there's no positive charge on there. So this here has a net dipole of 0, and it's non-polar. Okay? And that's it for that one. So let's go to number 9. We have 2 left. So actually we have 1 left. Sorry, this is the last one. HNO2. Notice this is an acid. So when you draw it, the H has to go on one of your 2 O's. So your central atom's an N because there's only one of them. You need to bond 2 O's off of them. This has 3 singles. Oxygen has 2 singles. So we're going to have an N with 5. We'll put an O over here. And the other O, remember, you want to get rid of have your maximum repulsion. So instead of drawing the second O down here, we're going to draw it over here. Okay. And so now what we've got is we need the H. And there's no ion, so you can't add any electrons here. So you can see, hopefully you'll be able to see, if we put the H here, now everything bonds really nicely. So that OH bonds, that NO bonds, and then this forms a double bond. So again, we have 2 central atoms. So let's start with N. So covering up this bond off the O, remember, a double bond is treated as a single according to VSEPR. So 2 bonded pairs, 1 lone pair off the N. So 2 bonded pairs, 1 lone pair is bent or V-shaped. There's the lone pair, 2 bonded pairs, 117.5 degrees. So you'll notice there's 2 bent or V-shaped. One has 2 electron pairs, and the other one has 1 electron pair. And that's why the angle here for this one is smaller, because 2 pairs pushes down these bonded atoms more than 1 pair. So these are going to get closer together, which is why the angle is only 104. These are a little bit further apart, which is why the angle is almost 118. Okay, so this is going to be bent or V-shaped at 117.5 degrees. And then this oxygen, if we cover up what comes off the N, we have 2 bonded pairs, 2 lone pairs. So 2 and 2 is bent or V-shaped, but it's the smaller angle one. So this is bent, V-shaped, but this one is 104.5 degrees. So this is a smaller angle. So let's start with the N. So we're going to draw an N with a lone pair. And then we're going to put a double bond off of this, and the single bonded O off of that. And because this is going to go off somewhere, I haven't put the lone pairs in yet. Let's cover that out. This has to be bent or V-shaped. So you could either bring your H down here, or you can bring it up here, which is what it looks like. Remember V's, when we drew our organic compounds, remember the line diagrams are V's. These can also form V's like that. So that's what your Lewis diagram looks like to proper shape. So now let's do the molecular polarity. So why did I put a positive on the nitrogen? Because nitrogen's less electronegative than an oxygen. So here's what we have. Dipole this way, dipole that way. We have two of them in this direction though. So what you've got now is one coming down like this. That's this one. This one we're going to add on in the opposite direction. So it makes sense that if you just looked at these two, they're going to go straight down. So these would go straight down. But now you've got one going this way and another one going that way. So what that's going to do is shift, instead of this here coming straight down, it's going to be off to the right a bit because you have two of them pulling this way. Hold on, I just realized I put a plus here. This is a negative. You have two pulling towards the negative this way, but only one on this way. So that's going to take your molecular polarity and set it off somewhere in that direction. So your net dipole is greater than 0. This is polar. Throw the whole mess in square brackets. Actually, no, I apologize. I thought we were dealing with the ion. I'm sorry. We're nearing the end here. I'm getting tired. So there's no square brackets around that one at all. So now let's go to the last thing is our VSEPR shape. So nitrogen has 3 of its p orbitals. So if you look at a nitrogen, nitrogen has a 2s with 2 and a 2p with 3. So what's happening here is the 3 singles in the p are bonding, but not the s. So we're going to draw 3 p orbitals. So one here with 1 electron, one here with 1 electron, and one here with 1 electron. So that's those 3 there. Okay, and the s we'll put up here somewhere. So now what we're going to do is bring in the oxygen. Well, this oxygen has both of its half full p's participating. So we're going to draw, where are we here? One here to bond here, and one here to bond here. So this O is this O with the 2 lone pairs around it. And then now all we have to do is bring in this oxygen. So this oxygen bonds to this nitrogen, whoops, to this nitrogen here. Bring in that electron. But the other bond goes up to an H. So you're going to put the H down here or up here. Well, according to our VSEPR, we're going to put it up here. So we'll put the dot there. And then all I'm going to do is bring in an H. And that is my valence bond diagram for this particular acid. So looking at it, I know it looks messy, but you're just following. So you have 3 single electrons, 1, 2, 3. 2 of them go off to 1 oxygen. So these 2 go off to an oxygen. So there's your 2 p orbitals of your oxygen participating. And then this oxygen has one of its p's going to the p of an N. So that's this bond here. And the other p going to an H. That's this bond here. No square brackets because this is not an ion. And I believe that was the last one on your sheet. So please do your best to try to understand this. I'm going to post the completed solutions to these examples here so you can go through and check them. And then by Thursday, I'm going to give you the second lesson, and it's a really important one because it's about carbon, and it explains how carbon bonds to form all the different organic compounds. The process is called hybridization, and it is probably one of the most important bonding concepts in this course. So I'm not going to skip over it, but it's really important that you watch that video to understand it. Okay. Anyway, thanks so much for your time. I know I went just over an hour. I was hoping to keep it at an hour, and then that's you're allowed 3 hours a week, so 1 hour and then 2 hours to work through the practice if you need it. And then I'll give you the other lesson, and that will make up the total time for the week.